Let's start chapter 1.1. I discovered when I was looking at my plan for this video that there was no benefit for me writing out stuff by hand, so I just typed up everything I'm going to say. So you can treat this like an audiobook if you want. So here we go. When we started derivatives, we said that f prime is equal to f of x plus h minus f of x divided by h for tiny, tiny values of h, and we want h to go to 0. And for example, if we're using like square root of x at x equals 2, we can explore what happens for tiny, tiny values of h. So let's go do that right now. Here we go. So I've got our central point x equals 2, and we'll say square root of 2. And so that's the square root of 2. And then we'll say my new x is my old x plus h. So we'll get tiny deviations from 2, and then we'll take the square root of all those values. And then what's my difference quotient? New f value divided minus old f value divided by h, or delta x. And what do we see here? As h goes towards 0 from the negative side, the value of the difference quotient seems to be decreasing and gets to be 0.35 something. From the positive side, the value of the difference quotient seems to increase. So the big question is, what do we think goes here, where we're getting a divide by 0? Probably 0.35 something, probably 0.353 something. That's our question. What value would make sense to go in that spot where h equals 0? Some people say let's average the values right before and right after it, so they would average this value and that value. And it turns out that's often close to right, but it's hardly ever exactly right, and sometimes it's way off, sometimes it's infinitely far off. And it depends on what value of h we choose. If I had chosen to use 0.001 and negative 0.001 here, I'd get a different value for the average of those two things. So we want a method that's always exact and that doesn't depend on our choice of h, something that's objective and immediate, sort of. So we're going to say the word for that before we actually say how to do it. So the word for that is the limit of a function as x goes to something. Above we had x going to 2. This arrow here we pronounce as goes to or approaches. If you don't feel like finding the special way to type an arrow in email, you can type a dash and then a greater than sign. Desmos cannot do the kind of limits we're working with here, unfortunately, so you don't have to worry about typing it in Desmos. This word limit is an unfortunate choice that someone made 200 years ago or so. We should really think of it more as a destination. So we're asking what is the destination of the y values of the function. And the function could be a difference quotient. It could be just a plain function without being related to a difference quotient. So we're asking what's the destination of these values as x approaches some number, or what is f of x approaching as x approaches some number. Remember, f of x is talking about the y values here. So as an example, if we say what's the limit as x goes to 3 of f of x, that's asking for what real number is a destination. I mean real number like rational number, irrational number. Real number includes rational or irrational. So what's the real number destination of those y values of the function as x gets closer and closer to 3, you could say, or you could say infinitely close to 3, or infinitesimally close to 3. Infinity is really huge, and infinitesimal is really, really tiny. So tiny it's basically 0, but not 0. But the point here is we don't care about the value of f at 3 itself, because we were getting a divide by 0, right? So we want some definition that tells us what number goes there based on the behavior near there, but not caring about whether I get a divide by 0 there or not. And sometimes we get a divide by 0 or some other undefined number, or sometimes we do get a number that seems to make sense, and sometimes we get a number that doesn't make sense. But regardless of whether f of 3 is undefined or indeterminate or makes sense or doesn't make sense, we want the limit to not depend on the value right there, because we want to be able to ignore it when we're doing difference quotients. Limits get used here in Calc 1. They also get used in Calc 2 and Calc 3. That's nice to know, right? It's not just a dead-end concept here. Like I said, the word limit is not a good word choice, but we're kind of stuck with it. Usually a limit in real life is something you should not go beyond, like a fence near the edge of a cliff or something. Or a doctor might say, do not let this patient get more than this much concentration of this chemical in their bloodstream. In math, y values can go beyond a limit and come back, and then even go beyond again and come back again. So really better to think of it as a destination. So the concept of limit is really useful, but it turns out limits don't always exist. They can fail to exist in three ways. We want limits to be the same from the left and the right. We want the destination to be the same regardless of whether you're coming at it this way or that way. So if that doesn't happen, then the limit does not exist. The function values might grow toward infinity or toward negative infinity, and infinity doesn't count as a real number. It's not an irrational number. It's not a rational number. So that's also a way the limit can fail to exist. Or the function might oscillate without settling down toward a single y value. That's more important when we've got x going to infinity, which we'll do later in the chapter. But we'll see a few examples of it here. And if a limit has any of these behaviors going on, we say the limit does not exist, and we just abbreviate that d and e, and then we say which of these three things is going on to be more specific, more helpful. Okay, so here in chapter 1.1, we're all about the meaning of limits, and we're taking an intuitive approach using tables and graphs. I'm trying to use minimal algebra, and we're not trying to do a lot of mechanics. We'll get to that later in chapter 1. But our next video, we'll look at a worksheet or handout with some examples.